Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
This session is called Functional Programming in the Wild, so we have a great session with some great speakers. And Don Syme is going to go up first, followed by Manuel Chakravarti, who's going to talk about some parallel Haskell work, and Antonio Sistinino following up behind, talking about some applications and using F# for various science and engineering applications, and also in computer science teaching. So I'd love to introduce Don Syme here. So I work with Don. I'm Kenji Takeda in the Microsoft Research Connections team, and I'm based in the lab in Cambridge, UK. And I have the pleasure of working with Don Syme, who's one of our principal researchers in the Programming Principles and Tools group. And he has, in his past, for instance, architected .NET generics, which some of you may be familiar with in C#, and also the person behind F#. And so today he's going to talk about some of the latest developments in F#. And so, Don Syme.
Am I on? Great. Thanks, everyone, for coming. I didn't get time to update my slides to this bright and white, so we're going to the dark, deep, dark colors that I usually use. So I want to talk today about, I want to give you a taste for what I think is the perhaps one of the most radical things going on certainly in strongly typed programming languages, which is what we're doing with F# 3.0 for integrating massive data sources directly into the language. And and this is coming out in product form. You can get it in Visual Studio 2012. I'll actually be demonstrating its use across platform today using my Mac here as well. And as we've been finishing up the product version of this work, it's sort of from practice to theory kind of thinking, which is what approach I like to take. Just do something radical and powerful from a product standpoint, and also then go and consider, well, what are the ramifications for strongly typed programming and programming languages in general? Where does this lead? What research opportunities does it open up in the future? And this talk is going to touch both on the practice in terms of the product and the language and the data, and then also the themes about reconsidering strongly typed programming for the modern information-rich world. First of all, one of the great things I love about F# from the Microsoft perspective is that it's open source. We very much embrace working with the open source community to do interesting things from the code base. We don't do development in an open source model. We do open source code drops that as we finish up the productization of a version of Visual Studio, we then go and have a chat with the lawyers and have a chat with the Microsoft management and just go through with the clearance process, which we're going through for F# 3.0. The F# 3.0 open source is in preparation right now, but you can go to GitHub, F# open source community on GitHub, and take a look at the F# open source code there. It's under Apache 2.0 license. You can compile it up on Mac, Linux, Windows. You can also host the compiler in the browser by compiling it as a Silverlight component. As you'll see today, you can get free open source IDE tooling for F# with MonoDevelop. MonoDevelop is a lovely little IDE which runs again on Mac, Linux, or Windows, and I'll be showing the use of that in just a moment. Okay. I want to start off with a quick retrospective on what programming languages research and its impact, some of the work on programming languages and its impact on Microsoft over the last 10 years. So a bit of a time warp from when I in a sense started my academic career. It started my research career in 1992. When I came to research in 1998, Microsoft Research, we started off by doing .NET generics, which went into C# generics. The yellow things are the various papers and specifications that have come out of this work, as well as the actual million plus programmers using C# today, all of whom are using this work, which came directly from Microsoft Research. Then we progressed on to sort of do the F# core language here in F# 2.0. Separate, not part of my work, but sort of based on the generics work. And I was tangentially sort of watching from the sidelines of C# Link, which is this wonderful use of metaprogramming, again, to tackle data integration into the C# and other .NET languages. We then did some work on F# metaprogramming. We did some work on cleaning up some parts of the basic functional programming model to make sure that pattern matching was extensible in the same way that everything else is extensible in functional programming languages. We did some work on putting units of measure checking into F#, which is just a fantastic addition to the type system to give effectively strong typing for numeric data throughout the language, if you want to use the unit annotations. And then we did some work on parallel programming for asynchronous programming in F#, and then that has been progressed, in a very direct line of work into a version of that work for C# asynchronous programming, which is coming out in C# 5.0. And we see I think this work has been very influential in you're starting to see C++ and other languages picking up on asynchronous programming as well. Okay, and the common theme here is all of these things are in some way or another related to the strongly typed functional programming research agenda, which has a long research history behind this work, and this is just one manifestation of it across in the sort of academia to industry kind of divide. So I like to summarize it like this. Back in 1998, it was all objects, and everything had to be a class. You had to use inheritance for absolutely everything. We then went through a sort of a slightly strange manifestation of that in aspect-oriented programming and all sorts of other fads running around. And anyway, that's fine. The dark days, the terribly dark days of 1998, where everything was objects and absolutely nothing else in your programming model but classes and inheritance, those and very weak type systems, those days are behind us. We have mixed object-oriented functional programming languages being industry standard. We see lambdas in C++ of all places just recently for good reasons too. We see JavaScript, a very functional, not strongly typed, but very functional programming language, and its approach functional first programming language. Scala and F#, of course, as well, being industry manifestations of functional programming. And Microsoft and Microsoft Research have, I think, really played a strong role in this transformation. A lot of other people have too, but I think we've played a pretty important part. Okay, so let's talk about F# 3.0. So the concept behind F# 3.0 is in some ways very, very simple, which is that the world it's no argument these days that the world is massively digitally information rich. You can see that in this sort of graph. This is one done by Kenji here, which is I was pretty amazed when I saw this. This is the number of open web-based APIs that are listed on the site programmableweb.com, okay, which is all about the web as a programming platform. And you can just see the absolutely exponential rise here in the number of open APIs that are available for use. And we wouldn't expect this trend to stop anytime soon. Okay, but there's a very strong sense in which our programming languages are information sparse. Okay, I sometimes use in many ways excellent language, standard ML, as an example of this, in that it's a great language. It's also in a sense a product of its times, in that the back of the language contains an index of library functions that are built into the language, and that library function is like read character and write character or something. And that is the full sort of information basis on which the language is constructed, okay, as an official sort of mathematical specification. That's fine from a mathematical specification point of view, but you get the sense that doesn't match the reality of information in the world around us, okay, that all the world's information that you're accessing from the outside has to be piped in through those two primitives. That doesn't seem sort of right in some way. Okay, so our programming languages are information sparse. You go to the .NET libraries or the Java libraries and you can't find the definition of a football player or a chemical element or a genome or a gene or any real information apart from sort of generic information adapters like XML or strings or streams of bytes or some other generic things you would find there. So this is a big problem. It's especially a big problem for strongly typed languages because these strongly typed languages like F# and Scala and others are wonderful information processing environments once you have the information in a strongly typed form. But if you have to pay all your cost to get that information into a strongly typed form through parsing and some sort of serialization frameworks or whatever else, then you're going to lose whatever productivity gain you pick up with the language. You're going to lose around the fringes, especially as the world becomes more information rich. And your programs have to interact with the digital world around you more and more. Then you're going to pay more and more of a tax at the boundary. It's fine if all you're doing is writing Fibonacci or other self-contained mathematical algorithms that don't talk to the outside world. But if your programs have to interact with this enormous information spaces around us, then we have to change what we're doing. So F# 3.0 is one manifestation of starting to fix this, and I'm going to demonstrate that and talk about these themes in information-rich programming. That's an interesting thing about, what paradigm are we really in? F# definitely comes from the statically typed tradition, but you'll probably be surprised at the amount of dynamically typed programming you can do in statically typed languages like F# and C#. So the world has also sort of changed. So if this was the world in 1980 or 1990 where these worlds were kind of being kept very separate, in a sense programming has grown an awful lot, and as it's grown things have sort of merged in between. And let me just turn those off. Okay. As things have merged, there's a bit of a search for how to make statically typed languages more dynamic, how to make dynamically typed languages more static, for instance, by adding type inference, which allows you to give good tooling support, perhaps give approximate errors or warnings within dynamically typed languages. So languages like Dart from Google lie in this kind of space. The C# and F# actually have a lot in this kind of space, and Java as well. There's many ways in which you can do dynamic techniques in those languages. And there's some interesting ways. The F# type providers is really about saying, okay, we're going to give up some things in static typing in order to gain a lot in terms of information access. So moderating static typing in limited ways. Okay, so a little bit about F# itself. This is our kind of mantra for F#, productive, supported, interoperable functional language to write simple code to solve complex problems. That was our kind of mission statement for F# 2.0. That slide hasn't come out very well, but anyway, you can see some F# code over the side. It's a little bit grey, but anyway, you see it. It's this standard functional programming kind of code. It's all strongly typed because you get type inference from over on the left, and there's some corresponding C# code which just gives you the difference in sort of succinctness of the coding paradigm if you're doing list and tuple and function programming. It's just one example of the comparison point. Right. It gets used a lot in practice for real industry things. Here's a quote from someone working for a power company in the UK, where they have a calculation engine that helps to balance whether the power stations get turned on or off based on various market signals that come into the system, and he gives some description of why F# was a nice fit for this problem. But we often see F# being used for the code at the heart of an application. There may be a lot of other code in C# or other languages or whatever, Java or anything, JavaScript, around that, but with some F# at its core. Okay, I'll skip this part of the language taster. This is just some examples of object-oriented programming here, and some little bit explaining that F# is an indentation-aware language like Python, so you have to line those things up like that. Okay, in F# 3.0 we add a notion of query to the F# language. The idea is that the bit in curly braces is the logic that gets executed on the server. Okay, so if this Netflix thing here represents a data connection to the Netflix service, then you can write a query to access that service, and the filters and so on will be sent as a metaprogram to the query in whatever form that it gets accepted. And so this is link queries in F#. Okay, so let's talk about F# 3.0. So let's switch over machines here. We're going to do this bit on the Mac. So PC3, here we go. Okay, pop this away. Okay, so here we have mono-develop. I'm going to display some data on the right, so I've squeezed the screen a little bit here. Mono-develop is, as I said, open source, freely available IDE for which you can use on Mac and Linux. It supports F# code. To get F# 2.0 with mono-develop, you just have to go to the add-in manager, go to the gallery, and install the F# language binding there. And on the Mac, mono comes with F#. So you just have to install mono, which is often, well, on the Mac, I guess it's not installed. So you install mono, and you install the F# language binding, and off you go. Okay? So to give you a feel for F# 2.0 scripting here, let's first load this little library here. Okay, this was something okay, great. So this little library just creates a window here. Oh, so what have we got here? We've got an F# script. So everything I'm going to be showing today is F# scripting. Okay, so the model here is you have a REPL interactive session down below, and you can use that to evaluate data. So if we can just do, we can say take the numbers from 0 to 99 here, and we can just highlight that code, and we hit Alt-Enter, and that evaluates and prints out the results in the window down below. Now, personally, I prefer to show results over in that window over there. One reason I do that is because you can show graphical objects in that window. Because I'm working on a Mac, we haven't yet lit up this show script, which is only like 10 lines of code or so, to display graphical objects. So everything I'm going to be displaying on the right is text. But when we go back to Windows and Visual Studio, you'll see that we can draw graphics there as well, pictures and the like. Okay, so we can take show on the numbers from 0 to 99 and hit Alt-Enter, and that displays the data over the right. We can extend that a little bit for x in 0 to 99, generate x and x times x. Okay, and we can do a bit of functional abstraction. The cube of x is an integer times x. Do that, and then generate the table of cubes here. There we have the cubes over on the right. Okay, great. Okay, now, let's just look at a couple of other things. First of all, yes, we can print. We can print. Hang on. Sorry. Let's get rid of this. I accidentally pressed build then. We'll just ignore that. Okay. Okay, you can print out down in the console below. We've done that bit already. let's create ourselves a form dynamically. We have that form there. We can add, use functions as callbacks to add, for instance, to the mouse click event, a callback which uses a different print function which prints out some data as part of it. So as I now click on the form over here, you can see the results coming out down below for the reactions to the form. Okay, let's get rid of this. Okay, but what we want to do is talk about F# 3.0. Everything you've seen so far is F# 2.0. And what I've done is the F# community recently have been updating the mono develop support to also support F# 3.0. And I took a copy of F# 3, a pre-release of F# 3.0 and put it onto the Mac and got it so that would work with mono develop here.
Can I ask a question here?
Yeah.
How does this mono IDE compare with the Visual Studio IDE in terms of running this?
It's very similar as far as the F# programming experience is concerned. Yeah. It's set up in pretty. We'll switch back to Visual Studio in a moment. You can get a feeling for how they compare. Okay, right. So F# 3.0. The thing we've done with F# 3.0 is to open the language so that we're using a provider model for libraries for the language. Okay, and this is, stop and think about this for a moment. Okay, so instead of referencing, normally when we have a library in a programming language, we're used to a library containing a fixed set of types and functions. Okay, that's what a library is. Okay, maybe it contains at the most 100 or 1,000 types, and maybe for each of those have 10 or 5, 10, 20 kind of functions associated with them. Instead, what we're going to do is make that into a provider model. Instead of having a fixed set of libraries to represent the stuff we can access, we're going to have an on-demand or lazily computed type space which you can program against. Okay, so it's a very simple idea of just, instead of having a fixed library, we're going to use the provider model for libraries. Okay, and what I'm about to show you is one example of using that provider model to take an information space in this information-rich world that we have around us and making it available in the programming language directly. And the information space I'm going to work on is called Freebase. So let's just take a look at this information space here. Okay, that's Freebase. Okay, so it's ontology, if you like. It's got lots and lots and lots of data. Okay, it's in a pretty organized kind of form. You can see you've got films, 40,000 updates to films last week, 1 million locations, 10 million entries under the music domain. Okay, there's a lot of information here. Wouldn't it be nice if we could program with this information? Okay, wouldn't it be nice if this source was just available to us in the programming language? Okay, so by using the type provider feature of F# 3.0, we can do exactly that. With this one reference to a type provider, which is only about, say, 1,000 lines of code, we're going to project in that entire ontology both the schema and the metadata into our programming experience. Okay, so we reference the type provider. We then create a data context to access the data store. And now we start to explore the schema. Okay, so what you're seeing here is dynamically drawing our types from the web ontology. Okay, so as I press dot, it goes and talks to that web ontology to bring in the types into the type system. Okay? Yeah?
How do you get the DLL from here?
How do you
get DLL, the library?
The DLL is a type provider. Yeah, that is the component. That is the adapter component.
Okay, so the website has to provide that to you?
No, someone has to write a DLL which deals with a protocol that is being used to talk. There's a particular, so we have a type provider for SQL databases. We have a type provider for the OData protocol, for example. Freebase uses its own protocol. So if a data service has its own bespoke protocol, then you have to write a type provider for that. Okay. But there are also very generic protocols like XML. You can do a type provider for XML data in general. Okay. Okay, so we're accessing Freebase here, and let's take a look what's in here. We can go to Science and Technology, for example. You can see there's quite a lot under here. Okay, we have all the different fields of science represented. And you can go to astronomy, for example, and you start to see collections of objects appearing. Okay, so this thing here under asteroids represents all the asteroids in that ontology. Okay, and you can go through the list. Okay. Okay. Now, because we're doing not just dynamic programming here, we're doing strongly typed programming. Then, as a programmer works with this data, they can get strongly typed hints about what the data is and what they can do with it. For instance, it gives us these summaries here of what's in the asteroids table. Okay. Okay, so usually we go to the chemistry and biology domains here, first of all. So let's take our show window here. And for instance, imagine our task is to get the names of the amino acids. Okay, so there they are. We can show the amino acids and they come up over on the right. Or similarly with the chemical elements. And starting with these data sets, it's a very usual process of working with data where you might, for instance, detect some, in the chemical element set, 2 names here don't have an atomic number listed. So as we're writing this code and we're working with the elements here, we have some chemical element X. Then we can do completion. And because we're working in a strongly typed setting, then the environment can know all the different properties that are available for the chemical elements. Okay, so as we look through here, and for instance, look at the atomic radius of the element, then we can see that it has an atomic radius here. And not only that, but the radius here, using the units of measure feature in F#, the radius is being converted into a value in meters. Okay, it normalizes into the SI unit system as the values come into the programming environment. Okay, so let's come through with these. So we'll, at the end here, finish up with our little display of the periodic table in order with the atomic weights of the most common isotope of each of the elements coming down here on the right. And now what I want you to imagine is how that data is trivial to discover in this environment. If I ask any of you to sit down with this environment, to start with data dot, and to go and find the names of all the asteroids, or go and find the names of all the chemical elements or their properties, like the boiling point of the data, you could do it. It's absolutely trivial. And imagine how would you do that programmatically in any other programming language that doesn't have the ability to embed an ontology of this size into the programming language environment. Okay, so we think of that as language-integrated web data. It's one example of using the type provider mechanism. Back in Visual Studio, over in Visual Studio, which is a pretty similar programming environment, I'm going to show you a second use of the type provider mechanism. Okay. So in this case, the type provider we're referencing is for the World Bank. Okay, the World Bank is a major provider of data. It's very interesting data from a computer science perspective because it's about big metadata and not big data. The data sets themselves are actually small. Okay, they're time series data for indicators that are provided by the countries themselves. So in the data, you can see the countries, and because we're working live with the database, it can provide us with the IntelliSense list for all the different countries that are available. we can choose a country and we can take a look what indicators are available from the data store. And there are thousands and thousands and thousands of these. You can look down the list here. Okay. And for instance, you can search for a word like debt, or you can, if you're interested in health statistics, you can look at, say, malnutrition in third world countries, and you can see the different data sets that are available for use. So we can, for instance, take a set of the countries here, evaluate that, and what I'm going to do here is pull together a chart of, we can go to the indicators, and we can search for the statistics to do with population here, and we'll take the population total here, and we're going to just make a chart of how those populations of the different countries on the right have grown over time based on that data drawn from the World Bank. And then we might do some usual normalization of that data and test whether that's normalizing correctly, and then normalize that from the starting point of 1 in 1960. And you can see how the different countries have the different population growth rates. Yeah? It's unique to F#. There's some similar, there's the idea finds expression in the Gosu language in the Java environment, which is sort of it's kind of an enterprise language where they, in business, this is an incredibly valuable feature, not only for open web data, but for businesses as well. You can imagine you're sitting in an enterprise. What you really want from a programming perspective is to have all the information in the enterprise that you're allowed to access at your fingertips in this kind of way. Okay, so the information-rich programming really has a strong tradition in the enterprise kind of world. Okay, and so yeah, that's what is driving that Gosu language, which is an interesting language. I'm sure it will find expression in other languages over time as well.
So that's a function of World Bank, who only provide this kind of data for that particular language? Or?
No, the World Bank provide a service. Okay, so just like we saw that, so World Bank provide an API. All of this is making web requests, ultimately making REST web requests to, like you'll probably see one example here, this one here, which if it comes up, oh great, okay. Yeah, hang on. Let's try one more try. Okay, that kind of data. You make a web request and it gives you data back. That's what's happening under the hood. But you can imagine how hard that would be to program with, okay? Because you'd be getting these XML blobs back. You'd be lost in just a sea of mess of data, okay? So it's about taking all that away and projecting it into the type system and programming it with it as if it's strongly typed data, okay? Okay, so, okay. Okay, I'm not going to have time to show this, but it's about F# data. Yeah, well, Kenji's encouraging me to show this, but I actually don't really even have the demo, actually. Well, let's try and show it, okay, just for Kenji. Let's see if this works up. It comes up. Okay. So one of the major things we've been working on, let's see if this comes up. Yeah, this isn't not gonna work, Kenji. Okay, one of the major things we've been working on is using this type provider mechanism to access Hadoop and Hive data. Okay, so you want to be able to point the type provider at a machine, such as this OpenF# machine, which is a machine on the Microsoft local network, and do exactly what we did before, get a data context for that machine, and be able to do strongly typed programming against the data on that machine, including querying that machine and sending the queries to the Hadoop cluster from this point. And that's something you'll be hearing a lot more about as we start to roll out this work over the next 6 months. Okay, so type provider is just like a library. It's an adapter between data services and the F# or .NET type system. You can kind of think of it as a form of on-demand type macros, but it is unique to F#. So the language itself doesn't contain any data. It's an open architecture for data adapters right into the heart of the programming experience, and you can write your own type provider. Okay. So to finish in the last 5 minutes, I want to capture some themes in information-rich programming. So the problem is that languages don't integrate data, and if they do, it's in high-friction ways like XML libraries for languages. Okay. So, or they use code generation, okay, but code generation doesn't scale to the scale of schema that we're beginning to see available on the web, okay, or even in the enterprise today. To try and generate facades for these kind of data sources is just not. You could do it to a certain degree. It's this industry standard way of working with this stuff, but it doesn't scale, the tooling can be bad, the strong typing, where you might get strong typing if you use code generation, but if you don't use code generation, you use lowest common denominator techniques like XML, and that's got a whole lot of problems in itself. So from a computer science perspective, I think I like to go back and look at the very basic equation of basic relation of programming languages. Now, this is where the programs are. So historically, there's just been a huge amount of emphasis on, new object models, are about modifying this part of the world, okay, working on E, okay. So type systems, and analysis and verification are often about working on the tau there. But I think there's one big fellow who's been actually forgotten in all this work, okay, which is gamma, okay. How do we extract the structure that is in gamma? And of course, what we're doing with type providers is pushing expressions into the gamma, okay, to allow us to draw out the latent structure that's available in that environment. But when you go back to many computer science analysis papers, okay, they start with this equation, that the environment at the start of the analysis is empty, okay. And for me, this is one of the biggest lies ever told in computer science, right? It's like saying our world around us doesn't exist. It's a complete denial of reality around us. It's a denial of the fact that programs have to interact with that reality. And this, I sometimes like to think of type providers as being the cult of gamma naught, okay? It's about saying that gamma naught is real. The programs have to interact with it, and we have to make that the massive information richness that's available in our digital world available to our programmers and not hide away from it and pretend that it's not there. Anyway, that's all meant to be a bit tongue-in-cheek, but I hope you get what I mean. Okay, so themes, big data. It's not just about big data and Hadoop and the like. It's about big metadata as well. Strongly typed languages and tooling surely have to have a role in taming this world of big metadata. We moderate strong typing a little bit. If schemas change, then you get problems, but often these schemas are very stable. So huge information spaces can and should be viewed as software components. We have to start, when we think about schema change, we have to think about that in the same language and terminology. We think about component versioning, and there can actually be a healthy interplay between this kind of thinking about these things. I think one of the key things about F# type providers is you can do multiple data standards with one simple mechanism. Okay, rich type systems importing rich metadata where it exists. Programming languages, it's about this gamma thing. How seriously does a programming language take gamma? Okay, are languages effective at working with external information spaces? Do they have queries, JSON, XML, type providers, ... This should be one of our key measures of programming languages. And I think we have to make sure we get a synergy between this world of programming type systems and information space metadata, and see the role of the type system as being about representing those information spaces. And so you can see things like, propagating units of measure information or propagating security information from the outside world in through the type provider, provenance, and many other things, rankings and so on, that you could start to propagate across this kind of boundary. Which leads to these kind of research questions. Can we design type systems which incorporate schema change policies? You might imagine a type system which says this is going to type check, but it only guarantees the type check for the next year, because the type sources that you're using come with a policy that says their schema is only guaranteed to be stable for the next year. Okay, so those sort of things, those sort of questions start to enter into the equation, and there's some other examples of the kind of if the metadata, for instance, is probabilistic and uncertain, then can we use that usefully in the programming language context? Okay, so to summarize, the world is information rich and our programming needs to be information rich too. It's big data to big metadata, and information richness, I think, for me anyway, has changed how we think about strongly typed programming languages without giving up on using strong typing, but just changing the perspective of what strong typing is and what the role it can play in taming that gamma in that equation. Okay, and thank you very much, and I hope you've enjoyed the talk, and we'll move on now to Manuel.
Thanks, Don. That's great. I think we could probably take like one question while Manuel's setting up. So does anyone have a question? Yeah.
How does F# compare with OCaml?
How does F# compare with OCaml? So the core language of F# is very much inspired by OCaml, and there's even a small subset that will cross-compile between the two. I think since that sort of F# 1.0 kind of subset, then the language F# has sort of progressed in directions which support the role of the language. So we've added object-oriented programming, which in some ways is some similarities syntactically with the OCaml mechanism, but it has an object mechanism that matches the .NET object system. And so in that way, it's got more similarities structurally with Scala, for example, as a language. The other comparison points might be, I mean, in terms of the actual F# programming experience, then it's very much, in terms of, say you're programming up a 1,000-line component in F#, then it's got a lot in common with OCaml. They're trying to keep that goodness of that core ML programming experience as a way of solving problems and expressing the solutions, particularly to problems that involve moving structural data around. So there are similarities in the core programming productivity experience between the two languages. But F# has gone in some other directions in terms of like information richness or object-oriented programming. Yeah. Just one question?
Yeah,
okay,
I think
great.
Manuel's now set up, so thanks a lot, Don.
Thanks.
So over to Manuel, who's come over from University of New South Wales, and he's going to talk about parallel Haskell, and this is a project which MSR supports and is working with a number of people, including Simon Peyton-Jones, another person in the Cambridge lab. So over to Manuel.
Thank you. Hello, everybody. Can you hear me now? Yeah. Excellent. So I only thought about setting up the computer, not myself. Okay, hello everybody. As Kenji already explained, I'm going to give you an overview about data programming using the functional language Haskell, and that is joint work with a number of people at the University of New South Wales, so Gabriele Keller, Sean Lee, Roman Leshinsky, Ben Lippmeyer, and Trevor McDonald, and also with Simon Peyton-Jones from Microsoft Research Cambridge. So it's all about parallelism, but parallelism has been changing very much in recent years. So it used to be all about special hardware, very expensive computers, and all about getting the latest every bit of performance out of those. But today, everybody got Perl hardware. Every PC, every laptop, every tablet, every smartphone has multi-core CPUs and multi-core GPUs. So how can we program them? Our goal is to provide a simple way to write Perl programs where the emphasis is, of course, on performance, because why would you write a Perl program, or why would you want to use Perl hardware if you're not interested in the potential performance increase, but where the overriding goal is really productivity, as it's usually in application programming as opposed to systems programming. And the way we go about this is to provide what some people call a semi-automatic way to Perl programming, meaning obviously we can't take any random sequential program and hope to make it in some magic automatic way into a Perl program. But given the programmer supplies us with a good Perl program, a Perl algorithm, then we provide compiler technology to translate that such that the application programmer doesn't have to deal with the messiness of explicit concurrency. That's the idea.
So here you're talking about parallelism within different core of the same. Are you talking about across different CPU?
So I'm talking about one program running at the same time on multiple CPUs or multiple cores of a single CPU or on a GPU. So let me give you some, just an idea of the type of applications we've been looking at. So we've been looking at graphics applications like ray tracing. And so we've got this little demo here. So just running on one core, you see a bit slow, right? The frame rate is not good enough. But if we use all 4 cores in this laptop, then you get a nice smooth animation. Okay, so that's one type of application, so graphics. Another type of applications come out of computer vision. So this is an application doing edge detection. In fact, it does real-time edge detection. So again, if I go and start this program, then the program is unfortunately on my desktop over here, but I can bring it over. So it uses the webcam in this computer, and you see there is a picture of myself and an edge detection running on that image as we are speaking. And yeah, you can change various parameters, but that also utilizes all 4 cores which you've got in this computer. And as a third example, we've been, before we go to the third example, let me tell you a little bit about the performance, because traditionally people are a little bit concerned. When somebody talks about functional programming and Perl programming, then the concern is that maybe these functional programs are quite slow, and then maybe you can parallelize them, but on an absolute scale, it doesn't really help you a lot. But that's not the case anymore. That might have been the case 10 years ago. So in this example of this edge detection algorithm, we are comparing our code against a library called OpenCV. OpenCV is an open source computer vision library, which, as far as I understand, is quite well optimized. And it uses SSE instructions to speed up computations even more. And it's the dotted lines, but it's not Perl. So independent on the number of threads, it's always the same speed. Whereas the solid line is the Haskell program. And you see if there's enough parallelism, so the image is big enough, with 8 cores, we break about even with this C library. So why is Haskell slower here? Well, we don't use SSE instructions. Currently, the Glasgow Haskell compiler, the development version supports SSE instructions, but the version we used for those benchmarks doesn't. Otherwise, we would cross over probably here. So you see we are getting the same ballpark, and we can effectively utilize the parallelism. And moreover, we can run the whole thing on a GPU. So the blue curve is the Haskell program running on a multi-core CPU, and the green curve is running on a GPU, specifically an NVIDIA Tesla that's 2 generations back, but at the time it was a quite powerful GPU. Yeah?
So what, your x-axis is the number of CPU threads?
Yeah, so the x-axis is the number of CPU threads, whereas the GPU, we always utilize the whole GPU using 10,000s of threads. Otherwise, a GPU is very, very slow. So the green line is really the whole GPU, and the x-axis only considers threads on the CPU. So you see the GPU performance is quite good, but sometimes for some applications you can get much more performance out of a GPU than a CPU. So in this case, some of that edge detection, the last 2 phases, are actually a fairly sequential algorithm. So the GPU program actually uses a mix of GPU and CPU code. But that limits the amount of scalability the amount of parallelism you can get out of that application due to the algorithmic properties. Okay, as a third application, we've been looking at physical simulations. So here, for example, at a fluid flow simulation. In fact, it's the fluid flow algorithm of Klaus Stem, which is quite well known in the graphics community, as far as I know. And we can run this as well. What happens here, I can put smoke or a fluid into an area and then apply a velocity, and we get this particle simulation. Again, that runs on all 4 cores on this computer. And again, I've got some performance figures. So if we compare that to that method was published in a SIGGRAPH paper, and that paper comes with an optimized C implementation. And the horizontal dotted line, which is our reference implementation, is the original C code, which hasn't been written by us. So it's really a well-optimized C, not just for comparison purposes. And the solid line, again, is the Haskell program. And here you see this solid line, repr minus N1, is on 1 thread. So actually, depending on matrix size, the Haskell program is already faster than the C program. That may come as a surprise to some people. So recent improvements in code generation for functional languages have gotten us to a point where we can actually generate quite efficient code. And then once we use parallelism, we are even faster. So again, we can run this on the GPU, and here the GPU outperforms the CPU by quite a bit because this algorithm can be mapped completely onto the GPU, and there's no CPU component. We've also looked at medical imaging. So here it's an interpolation of an MRI image. And there we don't have any comparison to C code because this was implemented actually by some other people using our system who found the algorithm was so complex that they'd rather implement it in a high-level language like Haskell than doing it in C code. Okay, so how does this all work? So there are really 3 key ingredients to our work. And one is that the first one is that we control effects. We limit side effects instead of controlling concurrency, which is the traditional way of doing it in an imperative language. The second one is that we use types to help the programmer express knowledge about the behavior of the program that they want to achieve, about the operational behavior, to express that in a declarative manner in the program. And that information is then utilized by the compiler to generate that highly efficient code. And we are working in data parallel framework. So let's start with side effects. So this is just a small example of a Haskell program. Haskell program, we have a function, an argument. In Haskell, you don't use brackets around arguments. That confuses people in the beginning. And on the right side, we have the function body. And on top is a type signature, consisting out of type arguments and type result. Now, as a Haskell programmer, you know there's no effect in this code. Why? Because the type is just a normal type, not saying anything about effects. So because it's pure, we know we could, these two sub-expressions here for sorting and computing maximum, could well be executed in parallel. There cannot be any race condition or anything semantically that's guaranteed by the programming language. So how do we know that? Because in Haskell, we track effects using types. That's just the type of normal integer, but once we prefix it with IO, or there's some other effect prefixes, if you like, as well, we know there might be an effect. And then the result is an int again, but there's an effect as well. And so if our original example is a pure function, whereas a function reading from a file obviously is not pure. It's got an effect. And that difference also appears in the way we program the bodies of the code. So that's the first important thing, that we know we can parallelize all these expressions. Now, the second component is that we use types to guide the execution of the program. So in particular, we use types to distinguish between the parts of the program which should be executed sequentially and those which might be executed in parallel. So we have this data type of arrays, which has three arguments specifying concrete representation of the array, the shape, which is the dimensionality, and the elements stored in that array. So let me just say a little bit about these representations which we use to index the array data type. There can be all kinds of representations. So on one hand, we can have a normal unboxed array, which is like a C-style array. But some computations, we want to fuse with other computations. We want to merge multiple loops into single traversals. And then we can indicate in the type that we want a delayed array, which is just a functional representation, a representation of an array as a function. And the shapes and element types, they are nothing special. So then operations operating on these arrays look like this. The types look like that. We've got a function here, a binary function, taking two arguments, and two arrays with that same element types. And that just applies this function element-wise to all the elements in the array, producing a delayed array. So we can fuse that into other operations. Or a more complicated function is a stencil computation for implementing convolutions, which we used, for example, in this fluid flow example. And then we can get quite sophisticated type description. This PS5 here, and I don't ask you to read this in detail, but it is a description, a type description of a partitioning of an array into the core array and four boundaries, which is the type of decomposition you need for efficient stencil computations. So how does the code look like? We don't have time for complicated examples, so let me just give this simple one. Here we compute a dot product by using the zip-with function, multiplying all elements pairwise, and then summing them up. And we get a type which tells us that this works for any numbers which we can store in these arrays. So let me just skip that. How do the GPU computations work? Currently, we are not at the point where we can take exactly the same code and run it on a CPU or a GPU, but they're very similar. The difference is that we use embedded computations for GPUs. So GPUs have quite a few restrictions in the way you have to program if it should be efficient. One is that you need to be careful about doing everything in a really synchronous fashion. And the other restriction is that you have to be careful with memory access patterns so that data access is efficient. And we achieve that by embedding a computation language into the main host language. And in this way, we can restrict the form of control flow which we allow in this embedded language so that we get these limited control structures. And then we use a generative approach for those people who've been in the talk about parallel programming. This is quite similar to the Python cheating example which they discussed. We use a generative approach to generate this highly tuned code. Okay, and the main difference here is really in the type again, namely that the result is an accelerate computation, a suspended computation, but then the actual code looks the same. And by the type, the compiler knows that this is an embedded computation and we can cheat it to a GPU. Okay, so how do we do on time? 10 minutes? Okay. So the third point that I like to address is that we are focusing on this data parallel programming model, which is well known to work for a certain range of applications, but there in traditional data parallel programming has some shortcomings. With traditional data parallel programming, I mean the models which are used in standard languages like Fortran or the CUDA language for GPU programming. And this same model really underlies the type of programming I've described so far. But what's the limitation? Let's get back to the dot product. We may want to use the dot product as a component in something bigger. So this something bigger here is a function which takes a sparse matrix and a vector and multiplies the two. So it's a sparse vector matrix multiplication. Now, here I used another language feature. This is called an array comprehension. You can read it like a set or a list comprehension. It says for every sparse vector in the sparse matrix, do whatever is on the left-hand side, namely compute the dot product between the second argument and that sparse vector, and then sum up all the elements in the dot product. So that's exactly matrix vector multiplication. But this array comprehension is supposed to be executed in parallel. But the sum, well, the sum arguably we might also want to execute in parallel. But then we have a parallel computation in a parallel computation. So that's nested parallelism. That's okay. Maybe we can have a special sum, a segmented sum to do that. But what about .p? Maybe .p is defined in a library. So does that already contain any parallelism? We don't know. So it may include nested parallelism. In traditional data parallel languages, well, you have to rewrite your program. You basically, as a programmer, you have to inline the dot product, or you have to know how it's implemented in the library to be sure that you don't get arbitrary nested parallelism. And that, of course, kills modularity. So how can we get around this problem? Well, one way of tackling this problem is to go to so-called nested data parallelism, where data parallel operations can be arbitrarily nested. And another benefit of moving from flat to nested data parallelism is that you get a handle on working with sparse and irregular structures, such as trees or hierarchical decompositions of space, such as you, for example, would use in an n-body algorithm, in a hierarchical algorithm like the Barnes-Hart algorithm to solve the n-body problem. In fact, you can, if you allow arbitrary dynamically determined nesting depth, you can quite conveniently implement general divide and conquer algorithms in a nicely, the traditional functional way, and run them in parallel. And luckily, there are program transformations. And going back to the seminal work of Guy Bleloch on the Nessel programming language, but which we extended in many ways such that this program transformation can now be applied to fully fledged languages such as Haskell. In that way, we get a handle on this modularity problem, and at the same time are able to work with much richer data structures. With data structures, really functional programmers are very much used to be able to work to, like trees, and would be disappointed if they can't do that in a parallel setting. But the compiler technology here is quite a bit more involved, so it's still quite experimental. But it is part of the Haskell compiler. So overall we get the following picture. On one hand, we, by going from flat to nested data parallelism, we gain a lot of expressiveness, although things get harder to compile. On the other hand, by going from general purpose CPUs to GPUs to more restricted hardware, one way we can realize that is by moving from a full host language, which is compiled, to an embedded language, which we do runtime code generation for. So, but at the end of the day, I think the main message out of all this work is types are really very, very important. We use types to distinguish effectful from non-effectful code. We use types to describe the difference between array representations, delayed arrays, decomposed arrays for stencil computations, and many more array representations. We use types to distinguish between embedded code and host code, where we can clip the embedded code. And we use types where this program transformation, which we use to implement nested parallelism, is also heavily based on types. It's in fact guided by types. So that's the important part. Here's a summary. And thank you very much for your attention.
Thank you very much, Manuel. That was great. That was great. So we've got time for a question or two while Antonio gets set up. So anyone got, yeah? Oh, two questions.
I see. What's Hackage?
Hackage is a package, a library database for Haskell. It's like Python or Perl has CPAN, the package repository, where you can get all kinds of Perl libraries. This is the same thing for Haskell. It's a Haskell.org is the one place where you get all Haskell add-on software to your Haskell compiler.
So if I want to use a functional language for scientific programming, should I use Haskell or F#?
I haven't tried doing any scientific programming in F#, so you would ask.
I think you should defer your judgment till after Antonio's talk. We're doing a half an hour of that as well, and then we can have maybe we can revisit that question after this next talk.
Enough.
That's fantastic. So perfect segue into Antonio's talk. So thanks a lot, Manuel.
Thank you.
Over to Antonio Sistinino, who's from the University of Pisa. Exactly, yeah. Exactly. So.
And we have foreign function interfaces, so you can always call one.
So Antonio is one of the leading members of the F# community. He's written with Don Expert F#, and that's just being updated for F# 3.0. And Antonio also teaches F# to both computer science and non-computer scientists. So over to Antonio.
Thank you, Kenji. So what I want to share with you today is an experience that now it's something like 3 or 4 years is going on in Pisa in teaching computer science to non-computer scientists, especially people from science and engineering, and sharing with you some thoughts about the results we got so far, and if F#, which is a full-fledged language, can be useful to teach to non-computer scientists. And I have found a lot of interesting things in doing this activity. I did it in many ways in several projects, so I will show you also the results of these projects and where everything started up 4 years ago. So the real point about programming is that in the beginning, they were just machine programming, and if physics, people in physics was, using punch cards and do a lot of heavy computation, and it was really about programming, knowing the machine. And then machine was not anymore the big problem, and there were algorithms. We were in need of a lot of algorithms. And in teaching and even doing experimentation, it was the focus to develop new algorithms. Nowadays, there has been a major shift, and most of the people programming is in the truth is doing software coordination. I mean, they tend to pick up algorithms and put them together in many ways. So it's a lot of time since I wrote my last while loop or whatever. I tend to say for each something, do this and that, and call this library and put the result in that library. And the algorithm has become so complicated and so focused on specific areas to the point in which it's difficult that someone from outside is able to contribute on that space. So usually you end up to Google somewhere and look for some algorithms that fits your problem. And this has been a problem for scientists, because scientists were used to build up their own experiments from scratch. They still do it sometimes. For instance, a Large Hadron Collider, they did it. But it's difficult to grasp all the complexity the IT infrastructure has bring into the game. And so actually it's quite challenging to figure out what does it really means to teach programming to scientists and non-computing scientists because of this, because actually they don't really care about all the bits we have just to have our computer run. Which is something interesting, because when I was young, in Mickey Mouse, and this is from Italy, they told me on Mickey Mouse that BASIC would have been my programming language. I mean, that was in the 80s. In the 80s, BASIC was in Commodore, was the way to talk to the machine. But nowadays things have changed a lot. And actually, MATLAB and Excel have found the most useful tool they use in science and engineering. And there are several reasons for this. The first one is that scientists and engineers want to be in control of their own computations, and they tend to hate quite a lot to have to interact with computer scientists. So actually there is an impedance mismatch on that space, and that's mostly because they tend to feel that they lose control over their own algorithms and thinking. And the other thing is that computer science and program development has become something like it takes time, but a scientist needs a much more high-frequency loop just to check and validate hypotheses and run code. And so they started using Excel in biological world. They use it a lot, and MATLAB a lot, and especially in engineering. They also use dynamic languages, Python, a little bit less JavaScript. They use it a lot, Perl for text processing, and many others. They still use C++, Fortran code, but they're really decreasing in numbers, because actually usually the cost to maintain the code is much higher than having a Python or something other different library. So things have really changed for them. And at some point you may wonder why this shift in the panorama. And my answer has been that software and computers are not anymore made for scientists by scientists and engineers. So in the beginning, computers were built to perform computation by scientists themselves. Nowadays, scientists, as military did also, use the tools developed for our people, not for scientists, as a tool for computation. So the main purpose of having a computer or a GPU that has been shown in the previous talk is mostly for gaming. And as an accident, it turns out that you can do matrices for some other computation, but it's really an accident. The main goal was to have fun for kids. So in this panorama, it has been really, really difficult for scientists to find the right way to develop their own code. And MATLAB and Excel have become their friend in this path. But it has some drawback in this space I will discuss in a little bit. So F#. When I found out about F#, I was thrilled because, first of all, it was a functional programming language running on .NET. I always thought that functional programming is a fairly natural way to do many things in computer science, but the truth is that it never made it through a commercial product or library, so it was rather frustrating to be a functional programming without the libraries and the ability to interact with technology. So my first impression was, wow, now I can finally and eventually have my graphics running on F# rather than C# and get the benefits of both worlds. I can get all the libraries and I get the flexibility of the functional programming world. Because it's a .NET language, it interoperates very well. We did it, and I will show you machines. So we built things and controlled them through F# code. There is type inference, which is a good thing because it gives to the language a flavor which resembles like Python or a dynamic language. And you can interactively evaluate expression, which is a beautiful thing. So actually, Don already showed this. And it's beautiful because you can even load and interact with C# code and do regression tests, for instance. So it's a good thing, not just in the space of coding and debugging your own program, but just testing or learn to use a library interactively, which is something I do quite often. It's efficient, which is a good pro, because usually, especially that's a tough question because it's more about .NET versus C++ rather than F# versus C++. F# compiles down to intermediate language MSIL and then gets just-in-time compiled into machine language and executed. So usually you can have 1.6, 2 as a scale in the average, I think.
So I think the usual terminology people use is, okay, if C++ gets 100, score of 100, okay? High-performance languages are in the 98 to 100% of C++, okay? Efficient languages are in the 80 to 98 range, okay? Dynamic languages land in the like 10 range, okay? So the real comparison point is like, I mean, C#, Java, they all take the same approach as F#, which is to get the 80 out of 100 rule for performance. Okay, and I think that there's a reason why Antonio isn't using the word high performance here, because F# doesn't necessarily always land in the 98 out of 100. You could use high performance C++ libraries for math. That's an actual recommendation. Do not do your math in F# code. Do high performance C++ code if you're doing.
It interoperates with C++.
Yeah, that was the other point. It's rather easy to hook into whatever library you want and call native code, even with special assembly instructions inside. So, but it feels like Python, and something that comes up is people is looking for high-level language. Even in computer games, they are looking for high-level language because actually you have to write down a lot of code, and the cost of debugging in C++ is so high, so that the typical model is to use coordination language, as it is, for instance, in the Unity game engine, which is fairly popular nowadays, which uses Mono as a game engine, a coordination language, and the C++ code is used for rendering 3D models and physics and everything. So, and it feels really like Python or MATLAB. And so my first experience with the Visual Studio integration, I said, oh, this is very much like MATLAB. I mean, I can write down an expression, evaluate, look at the result, and decide what I want to do, and then try again, which is very much like the workflow you find in this kind of tools. And so I thought that could have been interesting for them, because one of the big questions scientists nowadays have is how to share the results. Actually, MATLAB can be a problem because you need MATLAB to run the results you obtained. You have constraints on the hardware you can access because it should be MATLAB compliant. So I thought that IT was programming languages were mature enough to, at least in part, to cover the MATLAB story. Of course, MATLAB has a lot of high-performance algorithms and everything, and very good mathematics. And if you need it badly, you should use MATLAB. But in many everyday scientific job, I thought that F# was just fine. So I decided to try this approach. So that was 4 years ago, and I developed a tool which is called VS Lab, which is an add-in for Visual Studio that sort of complements this experience you have in Visual Studio and allows you to have dockable windows inside Visual Studio to have a graphic visualization, not just text inside of Visual Studio. Just to give you an idea of what it is, I have just a few lines here. So it's an open source project. It's available on Codeplex. So this is one of the first things I saw running on F#. It's a 3D function viewer made by Don. And actually, this is a dockable to Windows, so I can dock the graph, I can grab it, and this is DirectX, so this is full 3D. And the nice thing is actually I can change the function interactively, which is something I want to do if I'm a scientist. So convinced by this example, I said, okay, let's try and go into the field and convince people from other disciplines to use this kind of apparatus, and let's see if it's possible to teach them to use this thing. And of course, you can change parameters and whatever. I don't really care. Okay. So this is VS Lab. So VS Lab triggered the project, the first one, at the Centro Piaggio at the University of Pisa. And I did a graduate course to students in biomedical engineering. So it was so far from computer science, as you can imagine. And it was interesting as a course because they had some class on C code, because in their course of study, there is still someone in engineering that say they have to study C code because it's the right way to do programs. And they were interested in what? In imaging, in controlling hardware. And in many of these areas, the C is simply not satisfactory. I mean, people tend to use, in hardware control, yes, especially they use a lot of Arduino, and it's C-based, but on the visualization part, they tend to use MATLAB. And they tend to abuse of MATLAB because they badly need data structure, but actually MATLAB tend to convince people that everything is a matrix, so they do all sort of tricks to represent graphs inside matrices with very weird results. And so the goal, my personal goal was, okay, let's try interactive evaluation if it works for them. If they really use easily device, and eventually they can ship their own code, which is a pro for them a lot. And the result has been this one. So I have 2 preloaded videos. So this is a microfabrication machine, which is what I call a cell jet printer. I mean, they extrude a polymer on a surface to make cell grow on a surface and reconstruct tissues. So this is an example of the machine running. Sorry. Let's try to. No. It's dark. Sorry about that. Anyway, there is a needle that is controlled through the F-sharp control, and this is the interface that has been developed by an engineer. So this interface, with the help of a computer scientist, which is another pro. So actually, the biomedical engineer developed most of the C# code to all these buttons, all the drawing surface, and at some point, code sort of grown up, and she was unable to manage this complexity. So I found an undergraduate student that helped her, and they shared a language. So the computer science student helped her a lot in refactoring the code and having the code running in a proper way, but she was still in control of their own code. So the project was fairly successful, and it has been it led to a PhD, and so they use to build 3D cell structures, something like bones or stuff like that. So after that, I did that course several times, and I have many other experience to show to present, but we have no time. This year, I did another experiment with a class at Scuola Normale Superiore, which is a famous college in Pisa, to the class of science. Class of science as inside mathematicians, physics, geology, chemistry. And so the class was very heterogeneous, with a very different background, and I continued this way. I started with F# in teaching, of doing my teaching interactively. So I tend to open Visual Studio, type in code and discuss with them the code, and then send them the fragments so that they can test this. And I can show you, I think I have... this is the typical thing. This is the first lecture of the course. And what is interesting is that I found a way to discuss the topics which is rather counterintuitive for computer scientists, but which has shown to fit very well the mindset of a scientist, which is not really curious to know what's under the hood. And so it's very well ready to accept things such as, this is a type measure. So they can look at that. It's a type measure is a feature so that you can label numbers, and you get the standard calculus for measures. So it fits very natural, and the roots in ML, programming language, and in mathematics usually help them to understand what's going on. I mean, even the let construct is very well accepted, because usually they don't have any background in C-inspired language. So the result has been rather interesting, because in the second lecture I was able to discuss in detail with them something like this, which is take an infinite sequence of numbers, just filter the prime numbers, which is something difficult in a sense, but they did it essentially very well with this. So I was rather surprised on this experiment. And just to show you that it's not just a I also just received the feedback. So this is the first student. We finished the course a few months ago. They're working on a project as a final exam. And this is the first output from the class. It's from the geology class, which developed a viewer of SegY. SegY is a format the geologists use to store the data on the acquisition campaign they do on explosion under the earth, and they measure the signal propagation. And this is a typical representation they use in their work. And he's been able to, after 12 hours of course of lectures, he's been able to develop this. And that was sort of going to the web, fetch for a SegY library in C# that of course was there. Use it from F#, use the F# chart library that Don shown us just before to plot the graph, and that's the result. So I was fairly impressed. So actually, his problem right now is just to transpose the graph, and it is getting what they use it to pay for. A viewer for this actually is rather expensive, I found it. So that's interesting. So my experience has been quite good, but one may wonder if this is also good in computer science. So my experience is also in Pisa. We went back to ML teaching in the first year for many reasons. One of these reasons is F# was a driver of the decision, because F# being put inside Visual Studio was a sign that functional programming was taken as a sign that functional programming was mature enough for industry. So from Java, we went back to ML in the first year.
What's ML?
ML is a rather old programming language, which is sort of the basis for F# in a sense. It has been studied in the 70s, and it has been taught in many universities around the world as a functional programming language, and introduced many notions that are still there in many programming languages. It's been one of the roots. And then I personally use it in user interface programming course, and there is a very deep reason for this. It allows me to break down the UI development while still using a framework, which is the framework that commercially available, at least on the Microsoft platform, but also GTK Sharp, which is open source. And I want to show you an example of this. So this has been developed in lecture. I'll show you the code. It has been a lecture in this course. So I developed interactively the problem. So this is it's a very simple graphic control that shows balls that bounce. And you can introduce a new ball by drag and drop. And that was developed with the intent to show them how to develop a user control in Windows Forms, which is something you need to know if you want to do graphical programming. So just to get the paradigm behind this, this kind of programming. And the nice thing is that they felt useful the introduction of units of measure. They found it really useful, and so I show them pixels and seconds. So all the physics has been expressed in pixels per second, speed, and everything. And I was impressed that then their own assignment were written by using this, and it wasn't required. I mean, it was their own decision to use them. So it has been kept as a good sign. So just before I run out of time, I want to show you the reason why I'm using F# a lot, which is different just for teaching. And I want to show you, just to show this divide and make a fool of myself publicly. So this is a NeuroSky headset that allows you to essentially show the brain waves. So it's 1 point EEG that you can buy for, I think, $150. And so you can, so this is very risky because, you know, Bluetooth is faulty, but I'm going to try that. You have to hardwire your ear to get the current going through your skin. And I got this toy, and when I get a toy, I run with the iPhone application I got from the vendor. And second thing I did, okay, I want to program it. I mean, I'm interested in to use it for doing something like I don't know. And the problem was how to study what I was saying, and that's what I did it. I mean, this is, again, okay. So let's connect and hope everything's work. Yeah. And so there is a little bit of very few lines of code. So 90 lines of code that show, go on, there we go. So let's dock it here. Where is it? Oh, okay. So this is my, these are my brainwaves, or at least supposed to be. I'm not sure. So I'm still studying them, so there's no evidence it is working, but at least I'm just plotting the data I'm receiving from the serial port. And it's quite nice because in 90 lines of code, I've been able to do something. I mean, get a feeling of the sensor, get a feeling of how the sensor works displayed.
Where does the signal go to the computer?
Through Bluetooth and a library. There is a protocol, so you must know the format of the packets emitted by the. And I was already working, so actually I was interested in detecting the disappointment. They say, psychologists, they say it's possible to detect the disappointment. I was interested to get feedback because they say that this is can be noticed even before it gets conscious. So it's interesting.
So did I hear you say you had to do something special in attaching it to your ear?
No, it's just because you get a current, low voltage current. Yeah, so that's the ground.
You have to hurt yourself.
Yeah.
So what's that device for, originally for?
Oh, actually, they use it for to do mind control. Actually, I saw a parrot, a device we saw in the videos in the keynote, flew with the control of mind. So there are, these two are surrogates. So these are the raw data. These two are the attention and meditation signals. So these are what the vendor says is capable of capturing the relaxation and the activity signal. And using those, it's possible to discriminate. You have some amount of voluntary control on them, so you can write something that gets controlled by your head. Oh, it's sort of scary. Okay, so I think it's time to wrap up. So I found that functional programming, it has been really well accepted by scientists and engineers. So we're discussing to sort of consolidate this experience into courses that are not anymore experiments. and make them a lot of productive. So that's I think the real word. Still, I found that object-oriented programming is a barrier. So when I show them types and classes, sort of hit of a wall, and they stopped to they had a lot of problem to get the idea of object orientation. So I found out that they can easily use objects, but it's difficult for them to think in terms of objects and software engineering. So maybe after some time, but not now. And it's been a nice language to share the experience, and it also been a really good programming language for computer scientists. So if you have any question, let me unwire.